Hi everyone, and welcome to the video for the Module 8 lecture guide. So we have a lot of information from the last lecture guide that I've just copied here. We have the same vocab and symbols, we have the same ideas of what we want to do with a confidence interval, but we have a couple new things. So the three new things are we're going to be using the theory-based applet to construct confidence intervals. So we'll give the applet some information, it will construct the interval. We're going to use some formulas to do this, and it's very similar to what the applet does, but we're going to do one of these by hand, one of these methods by hand called the 2SD method, SD standing for standard deviation. And this is going to work for 95% confidence intervals. And so we are going to use a formula to build a confidence interval, just to explore it a little bit. And then we're going to see how the sample size, n, remember, that's our symbol for sample size, n, will affect the width of the confidence interval. Okay, so we'll get to see how we can control the width of the interval, at least in terms of trying to make it bigger or smaller, by changing the sample size. Okay, so remember, we've got a confidence interval, and that to us is the interval of plausible values for the parameter. So we've got two ways of writing this. We've mostly used the second way, interval notation. So number comma number in here, right? But there's also another way to write it, and so we can rewrite any one of these intervals as statistic, which will be the middle of it, plus or minus the margin of error. So that's the middle plus or minus how much you need to get to one of these outside numbers. And so this is just two ways of writing the same thing. The reason we do this is, well, we're pretty used to interval notation in terms of seeing confidence intervals, but if you're really interested in showing someone the statistic, your point guess at the parameter, right? So your one number guess at the parameter based on the statistic. If you really want to highlight that, and then you also want to provide the margin of error information, how off you think you might be, then you would write it in this first way. So when you see polling, so we're near an election time, you're going to see lots of polls. So you'll see it given as statistic plus or minus margin of error instead of as the interval. It's just a different way to look at it, and in the last video and last module guide, there were some examples of switching back and forth between them, and we'll just do the same thing again today. Okay, so what we did before was we constructed the interval by having all of these possible values for the parameter, and then we did a test on each one. We simulated what's the p-value, simulated what's the p-value. But that was terrible, so we're not going to do that anymore. So the first way we're going to do this is to use the applet. And so let me bring up the applet here. Okay, so we've got our applet, and there's really not much we have to do. It's pretty nice. So first things first, we want to do confidence intervals. So we're going to click that button, and you'll see we can choose our confidence level. So you can type whatever you want in here, 99, 95, 90, whichever confidence level you want. And then the other thing you have to be paying attention to is the scenario. And if we click this, we see there's 4 of them. Right now, we are looking for one proportion, one mean. Categorical, quantitative. Categorical, quantitative. And then depending on which one you choose, you have to just enter the information from your sample. Because remember, the sample is all we actually need to make a confidence interval. There is no hypothesis we have to set up, no null, no alternative. We don't need any of that. We just need our sample. So sample size goes in the first box. The second box is, since we're proportion, this is the number of successes in this box. In this box is the proportion of successes. So these two boxes actually say the same thing, so you only need to fill in one. Watch what happens with just a toy example. Let's say that we had 100 as our sample size and 20 successes. Now watch what happens to this third box. Automatically fills in with the proportion. Okay, so, or we could do, we've got 100 successes and, I got it right 20% of the time. Automatically fills in this box. So there's really only two pieces of information, p hat and n, or the count, and the other box will be filled in. So you just fill in whichever box is easier to fill in based on the information you have. If I instead say there were 20 successes in the prom, you put that in here. If instead I say the statistic's 20%, you can fill that box in. And then you just hit calculate, and you've got your confidence interval. So you can copy that into the work that you're doing. And again, I could play around here. Confidence interval. So that's it. That's how we're going to do this. So that's how we do it. Again, there's directions here you can check out. So let's try one. So example 1 says we want to know the proportion of people who suffer from a certain side effect when they're on a drug. We conduct a sample of 240 users and find that 5.2% suffer from the side effect. So we want to use a significance level of 0.05 for this. Construct the confidence interval. So what do? We go here, right? We are a proportion because we're talking percentages. The sample size was 240, right? And then 0.052 was our statistic. 5.2% of these people still had the side effect. And that ends up just being 12 out of 240, which you could check with a calculator if you want. All right, 5% significance level says 95% confidence level. Calculate. Here's my answer. That's it. I've got my confidence interval. I now would copy this and paste it into my document. So there it is right there. So that's a confidence interval. Boom. Our confidence interval is this number to this number, or 2.2% to 7.8%. It's a little easier to talk about these in terms of percentages when you're doing proportion most of the time, because it's a little easier to talk to someone about a percentage versus a decimal. We are 95% confident, because that was our confidence level, that the proportion of people who suffer from a certain side effect on the drug is between 2.2% and 7.8%. So we think the true percentage of people who are going to get the side effect is somewhere in this range. We don't know where exactly, but we think it's somewhere in here. And we have a 95% confidence with that. Okay, so let's try example 2. So we're doing a study of hypnotherapy to determine how effective it is in increasing the number of hours of sleep subjects get. We measure the hours of sleep for 12 subjects and find an average of 8.98 hours with a standard deviation of 1.29 hours. A says construct a 99% confidence interval for the mean number of hours slept for the population. So bring up our applet, we reset everything. I heard the word mean, so I'm going to change this over to mean. N was 12. Okay, my average was 8.98 from the sample. So remember, we just go back and we look for average of my sample. And then my standard deviation of the sample was 1.29. So let's go 1.29. So again, all I have to do, fill in the information for my sample. I wanted a 99% confidence interval. There we go. 7.8 hours to 10.1 hours. That's it. I grab it, I put it on the sheet. Okay, so you can see here, that's my answer. B says write this interval in context. C says what if the experiment was done instead with 24 subjects who had the same sample statistics? So let's go to B first. We are 99% confident. Let's see, so we could be up here. We are 99% confident that the average number of sleep hours, so that's what we were interested in, that's the parameter in the problem, for the population is between 7.82 hours and 10.14 hours. So again, remember, the form of this is we are blank percent confident. This comes from our significance level, our confidence level, that and then insert your parameter, average number of sleep hours is between, and then put in your confidence interval. Okay, so C says, what if the experiment was done with 24 subjects who had the same statistics? So instead of 12 people, we actually got the same data from 24 people. Let's see what happens. So all I do is I change this box to 24. It was 12, now it's 24. I run the confidence level, the applet to get the confidence level, and I get this new interval. Okay, so let's see if we can compare these together. Here are my two intervals. Right? This is with only 12 people. This is now with 24 people. We have to think about what happens here. Well, the interval got smaller. This interval is a smaller range of values, right? So I'm the same confidence level though, right? I'm still 99% confident that the true average sleep hours for people on hypnotherapy is between these two numbers. So same level of confidence, but I get to be a little more precise. How come? Why does it make sense that this new sample, I'm a little bit more precise in my answer, right? Why do I get to give a smaller range? How come I can be the same level of confidence, but I have a smaller range of answers now? So in every single way we could really think about it, my answer is better in the second case, right? So why is that happening? Well, let's think back. We've talked about this before. What happens when you increase the sample size? We are giving ourselves more evidence, stronger evidence when we have an increased sample size. And we've talked about this a few different ways, but I think the most natural way to think about it is to remember that there's still randomness involved in all of this. And so the more you do something, the less impact randomness can have on your results. So increasing the sample size helps us kind of fight against this randomness idea. And so that's what ends up happening here is we increase the sample size and we get a better, smaller range of values for the same confidence level. So what we can see here is if I want to try to take my margin of error down smaller, 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 I can try to increase my sample size. So the bigger the sample, the better in terms of trying to shrink your confidence interval as much as possible. It's just you have to balance that with other things. It's more costly to do a larger sample in many ways, more time consuming in many ways, so this is the balance you have to strike. And so this is called the 2SD method, and basically this is just based on all the work we had done in Module 6. So in Module 6, what did we discover? We said, look at all of these simulations that I've done. They all look really similar, right? They've got this bell curve. They're centered, right? Exactly where I know they should be. In Module 6, they were centered at the null hypothesis value because I told the computer, hey, this is the value that you should expect to happen the most. So, okay, that made sense. And then remember, we had formulas to predict how spread out each of these pictures would be. We knew these numbers would be where they are based on the formulas. So in Module 6, we talked about how to predict each of these pictures with some pretty good accuracy. So we're going to build off of that work here. And the way this works, the idea behind this is given by this picture here. So this picture should be something that you're familiar with from Module 6, right? And the idea being was that, remember, our simulations all seem to look like this picture. And what ends up happening is that anytime you have a picture like this, a bell curve like this, right? This curve is normal, but anytime you have a picture that's similar to this, we expect that 95% of the samples, remember X bars are samples, the statistics, 95% of the statistics, the data points, the dots in here, in the whole picture will fall in this red box. So we talked about this before. Remember, for this picture, we expect 95%, aka all the usual statistics that we're expecting to have happen, the middle clump, those all will fall in this red box. And how do I define this red box? Well, here and here are defined to be 2 standard deviations away. So if I have a collection of data, I know where the middle is, right here. I know the standard deviation. Remember, that just means the spread. It's a way to measure the spread. If I know those 2 numbers, all I have to do, and we've done this practice with the boxes before, is go, okay, here's the center, 1, 2 standard deviations above, 1, 2 below, and if I write those down, I will know where most of the statistics are supposed to lie. Most of this picture will lie between those 2 numbers I just calculated. 2 standard deviations up, 2 below. And we set this up so that this middle chunk of the picture is 95%. And remember, that sounds familiar, right? This 95%. Why does that sound familiar? Well, that is the opposite of our cutoff, 5% for the p-value. Because all that meant was, if you get a statistic with a p-value less than 5%, all that means is that your statistic was somewhere out here. It was in one of these tails, and these tails take up 5% of the picture. So if you were in a tail, it meant that you were in the outer 5% of the picture, which we called unusual. If you are inside the red box, then you're in the middle 95%, and we called you usual if that was the case. Okay? And so we, instead of having to use 95%, 5% as our cutoff, we realized that, oh, this line here, the actual boundary is -2 and 2 standard deviations away. So that's the idea of this. The idea of this, to kind of scroll down a little bit more, is that we are interested in plausible values, right? This is really important. We're interested in plausible values for the parameter. So if you give me a guess for your parameter, pi, mu, whatever it is, then all I have to do is ask the question, okay, is my statistic 2 or more standard deviations away? If it's too far away, then I'm going to say you're out in the unusual, throw it out. But if I'm looking for plausible, all I have to say is, okay, is my statistic within 2 standard deviations from the parameter? So let me say it again. Any parameter value that I could be trying to guess at, trying to find, as long as my statistic is within 2 standard deviations, this inner chunk, of that parameter value, then we're going to say the parameter is plausible. So we can write that down right here. As long as my parameter is within 2 standard deviations of my statistic, it's plausible. So if all I have to do is make sure the parameter value is within 2 standard deviations of the statistic, well, I can do that. That's easy. I can just say, where's my statistic? Go up. That's the plus sign, 2 standard deviations. Okay, I just grabbed all of the parameters that are within 2 standard deviations above. Okay, and then look left. Go left of the statistic, minus sign, 2 standard deviations. Now I've just grabbed all the possible parameters that are less than my statistic. And that's it. If I take my statistic and I go 2 standard deviations, left and right from there, I will grab all of the possible parameter values that are plausible given my statistic. Okay, so there we go. That's it. That's my confidence interval. Statistic plus or minus 2 times the standard deviation. So how do I figure this out, right? Like, what am I missing? I'm given the statistic, easy. 2, easy. Plus and minus, I can add and subtract. Multiply, great. SD, standard deviation. Right? I'm talking standard deviation of a picture like this. Do we remember how to calculate this? Well, yeah, in Module 6, we calculated the standard deviation of this picture, the spread of it, and it just ended up being this formula for quantitative, this formula for categorical. That's it. So these formulas we should recognize. They're the formulas for the standard deviation of the picture above. There's a slight change to them. We just have to be a little specific here, because maybe you're looking at this and saying, well, that's not quite the same formula because there's no pi in here. But remember, we don't know what pi is in this case. We don't even have a guess for pi. So instead of having a null hypothesis, pi equals 0.5, 0.33, whatever, that we'd plug in here, we instead of that use the statistic, because the statistic is supposed to be an approximation or a guess at pi anyway. So we use our statistic as a placeholder for pi in this case. And that's exactly what's happening up here too, right? Little s is the standard deviation for our sample. Wouldn't it be great if we knew what the standard deviation for a big population was? Of course. We don't, so we have to use little s. Same idea here. Wouldn't it be nice if we knew what pi was so we could know exactly what the spread would look like? Of course. We don't though, so we use p hat. Right? So we can do this. We've done this already. Statistic plus or minus 2 times, fill in the right formula. Boom. So let's look at an example, and then we'll come back to this warning. So the HTP is working to understand the scope of industrial pollution in the human body. Industrial chemicals may enter the body through pollution or as ingredients in consumer products. So in 2008, scientists tested blood samples for 20 newborn infants in the U.S. They were looking for some group of 430 industrial compounds, pollutants, and other chemicals linked to brain and nervous system toxicity, a bunch of bad stuff. Okay, so we're interested in looking at the number of chemicals in this certain list that we can find in newborns. We did our sample of 20 newborns, right? And we found an average of 127.45 chemicals in each of them. So the average per child in the 20 was 127.45 with a standard deviation of 25.97. So A tells me construct a confidence interval, 95%, and we're going to use the 2SD method here. So how do I do that? Well, the 2SD method, statistic plus or minus 2 times standard deviation. What's my statistic? Let's go back up. Find sample and average. Oh, here we go. Sample average of 127.45. That goes in there. Okay, plus or minus. Great. 2. I know 2. Write it. Times. Times is good. Got it. And then the SD here, the standard deviation, is given by the formula. Which formula? Well, it depends. Are we quantitative or are we categorical? I see the word average. I go, we're quantitative. So I use this formula right here. I'm going to grab this formula, hold on to it, drag it down, little s over the square root of n. What's little s? It's our sample standard deviation. Okay, that's right here. What's n? It's our sample size. How many babies or newborns did we measure from? Well, we measured from 20. So I type this into my calculator. I add to get this bigger number. I subtract to get this smaller number. Okay. Once I've done that, I've got my confidence interval, and I can talk about what this confidence interval means. So let's do that in B. We are 95% confident, because again, this was a 95% confidence interval, that the average number of industrial chemicals found in newborn infants in the U.S. in 2008 is between smaller number and bigger number. So we're 95% confident that the true average number of chemicals from this big list of bad chemicals that we find in newborn infants in the U.S. back in 2008 is somewhere in this range. Somewhere in here. 95% confident we're somewhere in here. Okay. So C says, if an acceptable level of these chemicals was defined to be 130, do we have evidence that newborns in the U.S. are safe on average? So what would it mean to be safe? We would want to make sure that, 130 or less was our plausible value, right? So we want to make sure the plausible values for this average amount of chemicals is 130 or less. Right? They're not going to be safe if there's a plausible value bigger than 130. So let's check out our interval again, right? So here it is, right here. I'm interested in trying to have 130 or less be my plausible values. And you see that does happen, right? 115, that's a plausible value. That's less, awesome. 120 is in here, awesome. 125, that's still fine. 130, okay, we're right on the border. But what's the problem? there are bigger numbers than 130 that are in this interval of plausible values. So it is plausible to us that the average could be 131, 135, 139. All of these numbers are plausible to us. And that's a problem. The fact that we have numbers that are plausible that are unsafe, bad, that tells us that we cannot be confident, we do not have evidence that we have a safe level. It's plausible, it's just as plausible to us that it could be 125 as it could be 135. Same level of plausibility to us. So because of that, we don't have any evidence of one versus the other. They're both in the realm of possibilities to us. So that means at this point, we can't say, yep, we're pretty confident it's safe, because it's plausible to us that we've got some big numbers as our possible parameter value. And since it's plausible, we're saying that's a possible number. And if that's a possible number, things are not good. So the only way we would really feel strong and have evidence about this is if every single one of our plausible values was 130 or less. If all of the plausible values were on the safe side, we would go, okay, we're feeling pretty good. But because we got even a single plausible value that's not safe, we have to say, sorry, we don't know. It's possible it could go either way. All right, so that's an important way to try to understand these ideas. So make sure you're thinking about these things. It's not just we can build a confidence interval, write it in context, but we've got to be thinking about what it means to write down these numbers as our plausible value. All right, so let's check out number 4. For a class project, a political science student at a large university wants to estimate the percentage of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Construct a 95% confidence interval for the percentage of students who are registered voters at the university. So, again, we can use our 2SD method, statistic plus or minus 2 times standard deviation. So just start at the beginning. What's your statistic? Go back up. What happened with these actual students? 500 students, that'll be helpful later. 300 out of 500. So my statistic is 300 divided by 500, which is 0.6. Okay, plus minus, cool, that's a symbol. 2, great, that's a nice number. Times, I write that. Standard deviation. What's the standard deviation in this case? Well, we got to go back up, scroll, scroll, scroll. Are we quantitative or categorical? Well, we were interested in the proportion percentage, so that tells me categorical. So this is the formula. I'm going to grab this formula, and we're going to scroll back down, and that's what goes right here. So square root, p hat, our statistic, which you already told me was 0.6, 1 minus p hat again, 0.6, throw it in, divided by n, our sample size, 500. I throw this all into the calculator, and I get the confidence interval, 0.56 to 0.64. So what does that mean? Well, we are 95% confident that the percentage of students who are registered voters at this university is between 56% and 64%. So there we go. That's our confidence interval. We're pretty sure that the true percentage of students who are voters, registered voters, is somewhere between 56 and 64%. Do I know where exactly? No. Am I 100% sure that it's in there? No. Am I pretty sure it's in there? Yep. Okay. C. The university has a goal of getting 50% of its students registered to vote. From the interval, do we believe they hit their goal? So what are we saying? We want to try to see if they have hit their goal of 50% of students, right? So there's a little implication here that you want at least 50% of your students to be registered. It's not that the university wants only 50%, right? That would be kind of a weird goal. We don't want more than half of you or less than half. We want exactly half. No, that's not what they mean. their goal in this case would be a minimum. If we can get to 50%, we'll be happy, but better would be, or more would be better. So why don't we think about what's happening here? Well, here's our confidence interval, right? So we think between 56% and 64% registered to vote. Where's 50%? Is it in here? No. So 50% is not a plausible value, which might make you stop and think, well, 50% is not in there, so that's not good. But let's think about this. All the plausible values are bigger than 50%. Right here. All of my plausible values are bigger than that. So not only does it seem like the university has hit their goal, they've surpassed it. All of our plausible values are bigger than 50%. So the university, however they wanted to get people ready to vote, they succeeded and they even surpassed their goal. So they went above and beyond, it seems, and got even more than 50% of students registered to vote. Again, we're not 100% sure that that's true, but we are fairly confident that the true percentage of students who are registered to vote is bigger than 50%. So they hit their goal and did even better. So this is just another example where we have some specific idea for the parameter we want to ask about, and we can use the confidence interval to answer that question. And the way we do that is we take whatever information we're given here and we look at our plausible values and then think about what they want to know. So in this case, did we get to 50%? It looks like it. It looks like we did even better than 50% because these are our plausible values.